So speed sensors, also referred to as velocity sensors. So what is speed? Besides the drug. What is speed? How fast something's moving, right? Huh? Rate of motion. The device capable of responding, of course, we know what a sensor is, right? Everybody okay there? Was that on the last test? If it's not, it's going to be on it. Okay, so these are the things we talked about that needs to be sensed. So what we're looking at now is what? Oh, I needed to highlight light. So we've already talked about those. Let me do that right now while I'm thinking about it. So here we're talking about speed. Some of these we have, some of them we don't have. We used to have the first one up there, but somebody threw it away. Then DC, AC, and then of course our instrument. Now these, all of them though, this is just the ones that we're going to talk about. So you might run into something later on that these are the way a lot of our, this is one of our licenses. I forgot what book I have to call. This is, we actually have this unit back there, the battery side of it, where we can actually check the speed of the motor. And what we do is we come up here and we put we just got a reflective strip on here. So this is going to work like kind of like a retro reflector, right? Because we're reflecting off a strip. But what we're going to do is, what's going to happen is the shaft is what's going to break the beam between the reflector. And what we can do on this guy is do time, how often it takes, how fast it comes to take for this strip to come along. And then we can do that in display speed. This is a variable reluctance encoder. This is used a lot inside your cars, in your anti-brake system, anti-lock brake system. This is used out around your rotor out there. What's nice about this thing is it can run in very, very harsh environments. So what we do is we have an electromagnet that's in close contact with the field. We have a magnet that's in close contact. And what we're going to do is we're going to induce a voltage into the winding around the magnet. So what determines the amount of induced voltage? Strength of the field. What else? Number of conductor loops. And 3. There we go. Speed of. So what happens when each one of these metal gears comes along, and this gear comes up here, the magnetic field concentrates. And then when it gets in the gap, the magnetic field is not as concentrated, right? So all of a sudden we have motion in the magnetic field, which we're going to induce a voltage into these conductors right here. So now we got motion just because the teeth of the gears going by, right? You understand? And now so we got this, we got a magnetic field, we got conductor loops, and we have a what? We have motion. Now it's the speed of the motion. So the faster these things go around, first of all, we're going to get a pulse. Every time we get a tooth coming around, we're going to get a watt out of it. We're going to get a pulse because we have motion. And the rate of the pulses would be equal to the watt. Would be equal to speed. You can understand this. I can slap this sucker on just about any gear. So I could use a gear, a primary gear that's always running into my like the output gear on my transmission, and I could use this to control the speed indicator up on my dashboard. So I'd almost bet that sucker uses a variable reluctance, because that guy can run in oil, it can run in transmission fluid, right? You understand, they don't really care. Very, very durable, anti-lock brake systems where you can sense, you hit the brakes and you can sense one wheel is supposed to be moving, and it does what? It stops. That's what happens, right? When you hit your brakes, right? You understand your wheels are not supposed to stop instantly. They're supposed to do what? They're slowly stop, and they're supposed to do it at the same time. If one of them stops, it means one of them's what? Locked up, and what does your car start doing automatically now? It starts doing what? It starts pumping your brakes. And sometimes you can hear that. On mine, a lot of times I'm coming off the interstate and I'm going real fast. When I hit the off ramp, I'll hit my brakes and I can feel my anti-brake, like the system pulsing the brakes for us. So that's what you're supposed to do. But a lot of people can't think about pumping their brakes when they're not stopping, when they're sliding. What do they try to do? They try to put their feet on the brakes, what? Harder. So this was first used in airplanes, by the way, years ago. They started coming up with anti-lock brake systems that eventually moved it into every car. And this is probably what they use. This is what they use. If you looked at anti-lock brake systems, they'll probably show this variable reluctance pickup out there on your road or somewhere, where it's actually picking up the speed of every one of your wheels. And you'll probably find one inside your transmission. If you ever did transmission work, on the main drive gear back in the back, you'll probably see a variable reluctance out there, and guess what that does now? That probably feeds your speedometer, so your car knows how fast you're going, right? Understand? Very rugged. Disadvantage, cannot measure slow speed. So even in your car, when you get down like below 5 miles an hour, your speedometer don't hardly do anything. So it has a real problem because it doesn't have enough motion, right? You understand? Should induce enough voltage to be able to be read at speed. Variable reluctance. And like I said, we used to have some of these around here, but somebody got rid of that. This is basically a pickup. So they're really, really rugged. And they can run off any gear, right? You understand that? All they're looking for is what? A metal gear with teeth moving around. So we don't have to have anything special in a gearbox to use these things. Then we have a Hall effect. Use a Hall effect speed sensor. And we know what does a Hall effect do? Magnetic field. And we looked at that way back there where we could fake this thing out and come up here and put a magnet. Then put the Hall effect. That should be uppercase, by the way. And then put a metal on this side right here. So let's say this is a gear tube. So what would happen is this is the Hall effect. This is my magnet. So when this gear tooth comes around, it would cause the magnetic field to concentrate through through the Hall effect, and the Hall effect output would go up, right? You understand that? And when it moved into this gap right here, it would cause the magnetic field not to concentrate. So it works very similar to a variable reluctance. The teeth on the encoder can be magnetic. So this guy right here can be magnetic. I've seen this too. Now the problem with putting your magnet out there would be what? You ever drop the magnet? Well, it's not hard to pick up. It's going to pick up something. It's going to pick up garbage all over the place. Basically work in a shop or work in a plant. So in my shed, if I drop a magnet, I pick it up. It's even hard to clean because you move it across and it just clings to it. So you'd have to isolate these. So having the magnet inside the Hall effect would be cleaner. But if we can seal this up and not expose it to other ferrous material or other material, then that could also be magnetic out there. And it would work basically the same way, right? But this example right here, we're using a magnet inside the sensor that's between the Hall effect and what it's trying to send. So this is working basically like the inductive. What's nice about this guy don't care about speed. Because it's not depending on the speed of the motion to put out enough voltage now to be able to detect. That would be the advantage on this guy. Of course, now we're adding more electronics, which means what? The cost of these would be higher than a variable. So if you don't need to detect extremely slow speeds, then the variable reluctance would probably be the route to go. If you need to detect the extremely slow speeds, then this would probably be the route to go. If you're the engineer, if you're the technician, you just make sure you replace it with whichever one you had, right? Are we okay? Then we have tach generators. These are basically just generators. They usually use permanent magnets as their field. And what happens, these are DC, so what determines the amount? So what we're doing on this guy is we're spinning a coil through a magnetic field. So what determines the amount we get out of the thing? The strength of the magnetic field, which we're not changing. These guys usually use permanent magnets, right? The number of conductor loops, we don't change that because that's built into the generator. So what's going to determine the amount of DC we got out of this? The speed of the motion. Pretty straightforward, right?
How you pronounce that word, Mr. Ruth? That T word?
Tachometer. Some people call it tachometer. Usually I blend it together. I've always heard it called a tachometer or a DC tach. A lot of people would just use the TACH abbreviation for this. So if you got on the internet and you said a DC tach or a DC tachometer, it would be the same. You'd go to the same place. Some people say tachometer, which I don't like. So we have a virus checking software on a computer, and it's called Kaspersky. And somebody kept calling it Kaspersky. Kaspersky, that's the way it's spelled, Kaspersky. So I went on their website and let them say it out loud to the person before they thought I was right. No, it's Kaspersky. No, it's Kaspersky. No, it's Kaspersky. Where's my camera? Surely I didn't close that thing down. Dang it. So we have a watt here. This is an MG set. So one of them's a motor. Here's a motor on this side. And they look the same. And that's what's so neat about DC motors. You can run them as generators, or you can run them as motors, which is pretty neat. These we use permanent magnets on, so you call these permanent magnet DC motors. That makes them a lot cheaper, but they're fractional horsepower. I was working on a Learjet one time. The thing landed when we was over in Japan, and they used the thing that got it going was a DC motor. And once they started, they switched the thing over to a generator. It was really neat. That's the first time I ever ran into that, and that's when it started making sense. So this is a DC tach generator, right? Or DC tachometer. Don't say GT, don't say tachometer, right? And what does it do? Puts out a what? A DC voltage that's proportional speed. So if I load it down, so my electronics, I'm trying to run this thing at a certain speed, and all of a sudden it tries to have another load. It's supposed to be putting out 10 volts, right? Putting out 7, what would I do? Would I put more energy into my motor to cause it to do what? Speed up. So this is a very, very popular. Starting to move out, but like I said, the problem we have with a lot of our older industries, like U.S. Steel, out of U.S. Steel, you're going to run into a lot of new stuff, and you're going to run into a lot of older stuff, because companies have a tendency not to replace things that's doing what they're supposed to do. Huh? Yeah, you're right. We ran into some stuff over at the weld shop, a pattern cutter that used big old torches, and they'd put a pattern out on a table, and it would follow that. That thing looked like it was ancient, but it did the job. It was neat. There's a lot of fire pits and stuff. The log holders for fire pits that was made on that thing. When I worked at U.S. Steel, guys, you could get almost anything you wanted made out there. Almost anything. So this is just a chart. You see these things are very linear of a typical DC generator. Now this guy, the maximum looks like it's about, 18 volts. And 18 volts would be, 6,000 RPM. So they're very, very reliable. Now if we needed to come into a computer, we could bring this into a, anybody know what that's an analog digital converter. And what this would give us would give us a binary number that would represent. So just about all your newer PLCs, we have some older PLCs that don't have this, but just about all your newer PLCs has analog inputs on, has analog to digital converters in. Because we live in an analog world, right? You understand that? A lot of them will have a digital analog converter on it also. But like to control the speed of a variable frequency AC drive, if you're going to control it with a PLC, it requires an analog input to determine the speed. Well, we have AC tach generators. So what's an AC tach generator going to do? So DC tach generators, the problem we got to do with it, we have with a DC tach generator, is that to get from AC to DC, what we have to do with the DC tach generator is we have to have a unit on the back of it referred to as a commutator. So it's got a ring that's got a bunch of slots in it. And as the voltage is being produced, what it does is it constantly swaps these things around, so it outputs the same polarity all the time. So by default, if I spin a magnetic field, a piece of wire through a magnetic field, what's it going to do? We have to have these things referred to as brushes. And they're basically made out of carbon, and they ride against the commutator, which means what right off the bat? We got one thing that's stationary in contact with something in motion. What's going to happen? Well, it's not going to reduce the voltage. What'd you say, Maurice? What'd you say, David? They're going to wear down.
The brushes will wear, right?
The brushes are going to wear down. So these DC generators and DC motors are going to require what we call preventive maintenance, which means you're going to have to do what? Now you're going to have to change them out. You're going to have to clean them. You have to clean the commutator, because after a while the carbon will wear out. You get between the segments, and then all of a sudden you get a short circuit. Also, these things are electrically noisy, because when it switches between the commutators, it always puts out a little spark, which is going to generate electromagnetic interference. So these guys are electrically noisy. So we don't like to use these around a lot of electronic equipment. But if you got them outside, you know, they're very, very reliable. Ours was in a pretty good distance between our control cabinets, so we didn't have any problem. So any of these DC generators and these DC motors are going to require what? Preventive maintenance. We can show y'all one back there that did get preventive maintenance. Let's go see if we can find it right now. So, this actually came off of, a floppy disk, a 5 1/4 inch floppy disk, if y'all remember those. So this is the little MG set. And instead of being DC, this is AC, and it's all contained in one unit. So what would an AC TAC generator have over a DC TAC generator? What would be the advantage? No, AC over DC. So why don't we just go back and look at over there that's required for a DC? Brushes and commentators. So AC TAC generators don't have brushes and they don't have commentators. Which right off the bat, and that's one big advantage an induction AC motor has over a DC motor. There is no what? Commutator, and there's no brushes. So once we figured out once they figure out, used to, DC motors were predominant where we needed to have control of the speed, precise control over the speed and torque of the motor. Until they figured out how to do that, DC motors were everywhere that required those two requirements, that provided needed those two requirements. Since they just figured out how to control the speed of AC motors, then AC motors are dominating speed control circuits now. By using variable speed drives. So AC has an advantage over, it does not require the commutators and it does not require the brushes. So there's very little preventive maintenance on these guys, right? You understand? What these guys are going to do, and so here's the TAC generator. I'm going to slow it down so y'all can see what's going on. So to visually see this, I'm hooking this up to an oscilloscope. So the advantage of an oscilloscope is we get to see exactly what's there. Just look it around with it. And also it looks impressive if you know how to use one of these things, don't you? See all the knobs? A lot of knobs scare people. There's actually something there right now. It's just that I got it running, so I got myself going too fast. I mean, going too slow. And so you can see the AC. This is 0 right here, so we have a positive alternation and a negative alternation. I'm going to increase the speed of the motor. And the first thing you notice is they're getting closer together because the frequency is going up. And frequency is the rate of the cycles. And then, of course, the faster the cycles, the closer they're going to get together in time, right? You understand that? So what a scope does, it measures voltage relative to time. And right now, we're close to the refresh rate on my camera, so that's why it looks like it's, y'all know cameras don't take one picture, they're taking a series of pictures, right? You understand that? But you notice, as I speed the thing up, the voltage goes up, and not only does the voltage goes up, but also the frequency goes up. So I'm going to have to increase the speed of my scope, and pretty soon, the refresh rates on the scope and the refresh rates of the camera don't interfere with each other. So I'm getting closer together means the frequency is going up, which is frequency goes up, time goes down. You understand that? So we'll change the speed of the scope and increase the number of volts we put per division. I've done something because it won't let me go greater than 500 per division. At 5 volts per division, that would still be 5, 10, 15, 20, 25. That's still 50 volts peak speed. So we got two things we could use here. We could use the frequency of the pulses, right? How fast they occur, or we could use the amplitude or the speed. We could very easily, with diodes, guys, we could very easily convert this from AC to DC, but we would do it with solid state. As soon as we say solid state, it means no moving parts. So a lot of times they'll use an AC tach generator and they'll bring it into a DC system just by converting it to DC before we get in. Then we have incremental encoders. We're already familiar with these guys, right? So incremental encoders are really cool. We can use them to sense position. We can use them to sense direction, and we can also use them to sense speed. I don't know if it still works or not, but this is the easy data where we can use it on the. So we already know how these things work, right? So we've got an incremental encoder, it's got a bunch of slots, a bunch of lines. It moves past an optical sensor or some type of sensor that senses the pose. And then, of course, the rate that they're coming off of will give us the speed. So the RPM would be equal to the, number 2. Simply figure the speed. So first of all, what we have to know about the incremental encoder is the number of peaks we have per revolution. Right? Does that make sense? The more peaks we have per revolution, the better is the resolution of the speed. Does that make sense? Yes, ma'am. Resolution, we mean preciseness, right? How precise it is. So something that has higher resolution means it's more precise. So if I only had 1 pulse per revolution, then it would be harder to calculate the speed precisely than if it had 1,000, right? Does that make sense? So we could use this as an encoder, but we would have to know how many pulses we get per revolution. So we could use this AC right here. I don't know if it gives us 1 cycle per revolution or 2 cycles per revolution. So the problem we have is normally we don't use this guy right here. I have to tell you why, because normally when we measure the frequency, we don't really measure the frequency, we measure the time. So when we're talking about a repetitive waveform, we have something we refer to as frequency. And what is the frequency? Yeah, it's the rate of the cycles. Now this could be AC, or it could be also what we get off the incremental encoder, which would be this right here. So these pulses are going to be occurring at a certain rate. Everybody okay? If you've had AC, you've done this, and we talk about this in digital also. What we call the period, anybody know what that is? Yeah, the time for one cycle. So I guess we should put cycle. What's a cycle? Yeah, technically it's one repetition of a repetitive waveform. Yeah. For example, Alabama Power, they transmit cycles. Anybody know the frequency for Alabama Power? Yeah, 60 hertz. By the way, 6 hertz, which we abbreviate with the uppercase H, lowercase b, stands for cycles per second. So if we know the speed of the cycles, if we know how many cycles we have in 1 second, so this is cycles per second, how would we calculate the time? No, this is, we're just talking about. Yeah, I would take the time, 1 second, and I would divide it by how many things we're putting in that 1 second, right? So the period is equal to 1 over the frequency. So the period for 60 cycles, and I'm going to put it down as T, would be equal to 1 over 60, which would be equal to 8.33333, goes on forever, milliseconds. I'm sorry, that's 16.6666 or 16.7 milliseconds. I was thinking for an alternation. So if I knew how long, if I could come over here and I say, I came over here and I counted one of these teeth right here, and it was passing, let's just make up something, in 10 milliseconds. How fast would it go? How many revolutions per minute would it go? So frequency is the opposite of time. Time is the inverse of frequency. So if I know the time, I can calculate the frequency is going to be 1 over the time. And of course, the time would be equal to 1 over the frequency because they're just opposite each other, right? So anytime you take the reciprocal of something, what do? You flip it. You find the inverse of it. So that would actually be from here to here, because that's when we get our pulses. So let's say this would be 10 milliseconds. So what I would get out of my scope is I would get something that looked like this, and that's what we're looking for is 1 cycle. So this would be when the blade covers it up, this would be when it's uncovered, and this would be when it covers up. So this right here would be 10 milliseconds. And so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 blades. But what I would do with my oscilloscope is I couldn't measure the time for 15, I would measure the time for 1, right? You understand? So first thing I would do is calculate the frequency. I would do the frequency. Frequency is going to be 1 over 10 milliseconds. So let's get our calculator out and do this, because this will be on the next test. So what I'm going to do is I'm going to give you, this is right off the Siemens test, by the way. Siemens level 1 test, they give you this exact same question. They give you an encoder, an incremental encoder. They say 1 pulse gives me this duration. What's the speed of the motor? So what would the frequency be? 10 milliseconds? Huh? Frequency is 1 over time. I'm giving you the time for one cycle, the time it takes to get from this guy to the next one. That's what we would measure right there. And I said it was 10 milliseconds. So I was saying, okay, that would be the period of the cycle, right? You understand that? Now we need to calculate the frequency. What would the frequency be? It's going to be 1 over 10 milli. What's 1 over 10 milli? What's the reciprocal of 10 milli? Huh? 100. Right? Now this is going to be hertz. My frequency, now we got to figure out, okay, if it's here, right, you understand, something don't look right. Huh? Yeah, y'all understand that. That's just basic. So you say if I do something at a certain rate, so let's say I do 10 and I'm doing them at the same time. I can do 10 of these things in 1 second. Then how long does it take to do one of them? Well, you would take the reciprocal, right? Well, how long, if I did one at this time, how long would it take me to do 10 of them? Well, you just do, understand what we're saying? So they're the opposite of each other. So frequency and time are exactly, they're inversely proportional, which means what? They're exactly opposite of each other. So if frequency goes up, what happens to time? Well, what if time goes up? Frequency got to be going down, right? You understand? So the way we find the opposite of it, and this is why just about every calculator has what we call a reciprocal. And what's the reciprocal key? 1 divided by x. So that means if I know the time, I can just enter the time, hit that reciprocal key, and it'll come up and give me the rate of the pulse, right? We okay? Huh? Okay? Huh? So what do we got? So Joe Bear said 100 hertz. That's what you came up with? So you okay, Jackson? Not a kilohertz. So 1 millisecond will be a kilohertz. Okay. So now we know. Now we know the rate of these things. But this is still cycles per second, right? You understand? So how long would it take for 1 revolution? Of this example of here. That was 10 milliseconds for one of these guys.
Oh, wow.
How you do?
I can, there ain't no way in the world I can take 10 milliseconds and multiply it times 15 and come up with
That's one revolution.
Now, this is not-
60, so
No,
one
no,
revolution,
this is for one of these blades right here. This is how long it takes for one cycle off of one of these blades. Right? And how many blades do we have? We have 15 of them.
We'll be 150 minutes, same with three.
Yeah, something's going, these formulas don't look right. I'm trying to figure them out. Oh, I'm sorry. This is frequency. This is frequency over the number of feet. Right? Right. So we got, what would be our frequency? 100 hertz. Right?
Uh-huh.
divided by 15. 6.66.
We're trying to, what are you asking? What are you asking for RPM?
We're trying to figure out the RPM.
And this is times 60.
Well,
RPM is 6.
well, first of all, we got to, what does RPM stand, what does RPM stand for? Per minute. So right now we're dealing with, right now we're dealing with seconds, right? You understand that? Okay. That makes sense? Yes or no? So what we're trying to do, if we're getting one pulse every 16 milliseconds, right? We're getting one pulse every 10 milliseconds, then it would take, what? 1,500 milliseconds for it to make a complete revolution? Right? 1.5 seconds per revolution.
You're asking how long it takes to revolution.
Well, that's what we're trying to do, but we got to go from a time to, we got to go for a time over to revolutions per minute, right? So if we can calculate the revolutions, per second, then we can do what? So everything we're dealing with now is in seconds.
We'll go from seconds to minutes.
We go, to go from seconds to minutes, we just have to do what? Multiply it times 60, right? Does that make sense?
Yeah.
Okay. So if it takes 60 revolutions it takes 1,500 revolutions, right? 1,500 milliseconds per revolution. If we take the reciprocal of that, that would give us a revolution, that would give us our frequency, right? And then if we multiply, that gives you 1,500.
We use it as hertz is our frequency.
Yeah, because what we have to do is we have to get this thing into revolutions per minute. So we're going to go to cycles per second to revolutions per minute, right? Does that make sense? Yes or no? So we got 10 milliseconds, right? All right. Then we multiply that by 15. Why 15?
So how many teeth it is?
Okay. Right. So that would be 15 milliseconds per revolution, right? So this would be what?
RPM per minute.
Yeah, revolutions per minute, not RPM per minute. Right. You can call me Ray, you can call me RJ. So this formula, that, first of all, we calculate the time per, so we took 10 milliseconds, which is the time for one pulse, right? You understand? Then we multiplied that times 15. That would give us, so we took, I still had 400 in there. So we took the time per pulse, right? This would give us one pulse per tooth. Then we multiply it by 15. That gives us this number of pulses per revolution, right? Then I took the reciprocal of this. This would give us the time for one revolution. So this would be 6.67 revolutions per second. Because everything we've done so far is in seconds, right? And then I would take and multiply this times 60, which would give me 400. Huh?
I took that 100 hertz and divided it by 15.
Well, that's what we're going to see. So this is the way I saw it in my head, the way I did it. But I think the other one's going to work out too. So the frequency would be what? 0.01. So the formula I think is right. And it's a lot easier than the way I saw in my head. So 0.01. Sorry guys. 0.01. Right? Then the formula says do what? Right? No, this is not frequency yet. That would give us this, right? Divided by 15t, give us that, times 60. Comes out to be exactly the same. So the formula is right. What they're doing is, we took the frequency last, where this formula takes the frequency first, right? Understand? So this one's a lot simpler. So you just do what? Take this, right? Take the reciprocal of it. That would give us per second, right? Then what we do, divide it by the number of teeth, which gives us that, which is revolutions per second, because everything's in seconds, right? Frequency's in cycles per second, right? The period is in milliseconds, right? So what do we need to do with this? Multiply it by 60, and then that will give us the RPM. So we'll see if we can do this here. This is our, so this is what we have. This is a gearbox. What time is it?
2:45.
Because we need to have time to do a little lab today. Because I know. Okay. So this is what we have. This is a servo motor. Today, what's a servo motor? It's motor that provides feedback. So, why I asked Joe Bear, tell them why, Joe Bear? Yeah, they asked about it at Honda. So a servo motor is a motor that provides feedback. This is a geared motor. So this is a gearbox on the end. And what does a gearbox do for us? It can do one of two things. We can change directions with a gearbox, but we're not talking about that. It's either going to increase speed and decrease torque, or it's going to increase torque and decrease speed. Because work in equals work out, right? And work is force times distance. And of course, the force of a motor is in torque, which is a twisting thing. So torquing, if work in equals work out, right, you understand, and it's force times distance, or force times speed, if you increase the speed, then torque has got to do what? It's got to go down. So a lot of gearboxes, so this guy is a torque multiplier, so it's going to be a speed divider, right? Understand? That makes sense? So this is a speed divider. And it's got so many wires on it because two of the wires is to run the motor, and then the other wires is for the quadrature encoder. So this is a quadrature incremental encoder. So what advantage do we have on an incremental encoder, especially a quadrature incremental encoder? What things can it provide? Speed, position, and direction, right?
You said it's called what type of circle?
Servo motor, not servo. Is that what you heard? So anything like a servo system, this is something that this is a system that provides feedback. A servo motor, I don't see my PowerPoint, guys. A servo motor is a motor that has the feedback built inside it. So servo, S-E-R-V-O. And this is a feedback or closed loop system, right? So a servo system is a closed loop system. And what do we mean by a closed loop system? So what's the makeup of a standard control system? We have what?
They don't require feedback.
Yeah, control and output. Now, if we take a output and feed it back into control, then this would be called a feedback system. It's also called a closed loop system. This is not an open loop, and it's also called a servo system. Now, what do you think provides the feedback? Sense.
All right, so I had that same question in operating program. They have a closed loop and open.
An open loop means no fit. What advantage does a closed loop have? Well, a closed loop system, you tell the devices what to do, and then you check to make sure it's done correctly. An open loop system, you tell it what to do, and you take for granted that it's done. Yeah. You have no way of knowing unless you're sitting there looking at it, right? Now, what advantage does a closed loop system have over an open loop system? Well, you verify that what you told the motor to run at a certain speed, and you check to see if it's running at that speed, right? If the motor tries to slow down, you automatically speed it back up if it's right. So your cruise control, if you got a cruise control in your car, it is a closed loop system. You establish a set point, an input, and then if the car tries to slow down, what does the closed loop automatically do? Fix it back up. What advantage does an open loop system have over a closed loop system? Cheaper. Thank you. A lot cheaper. So if they can do it open loop, they're going to do it open loop. But if they can't do it open loop, they're going to do it closed loop. Right? That makes sense? So this is a servo motor, which means it's a motor that has the feedback built into the motor. So just about all the motors used on robotics and in speed control systems are servo motors. So it saves us from having an external source. So this guy here has a quadrature encoder on it. It's a Hall effect encoder. So it's got two Hall effect sensors. It's got a rotary magnet that goes north, south, north, south, north, south, north, south. And it's got two Hall effect sensors that's offset by 45 degrees, which gives us the different pulse. 90 degrees. So it's Hall effect. It's a 131. We got a 131.25 to 1 gear motor ratio. So the output shaft would see my encoder. It's got 16 pulses per revolution. I'm going into a 131.25 gearbox. So my gearbox is seeing, so I'm seeing 2,100 pulses per revolution on that thing. So my encoder, even though it's got 16 slots back here, it's seeing it as 2,100 slots. That makes sense? Because of the gearbox. Y'all understand that? Yes or no? So it's DC powered. The encoder, we need to power it something anywhere between 2 and 20 volts. The motor power, to adjust the speed, of course, the maximum voltage, we should put 12 volts. So this would be our formula, right? Frequency that we measure divided by what? Times 60. Now what we can do is we can come up with what we call a transfer function. So what do we do there? Is I go ahead and take the known. If I move the 2,100 over here, I take 60 divided by 2,100, and then I can come up with a known. This is the transfer function. Everybody understand that? So how did we do that? See that? So this was what I would put inside my computer if I measured the frequency. So y'all take another 10-minute break while I hook this up. So here's the connection. So the red and black wire, this is where the motor goes. And that's really not the polarity because it's a DC motor. We can change the direction just by changing those two wires. And then we have a power supply for the encoder. And then we have a common or ground common for the encoder. And then we got an A and B output for the two encoders. And if you look, I think the A leads to B if it's in the clockwise direction. That's given somewhere, but right now it didn't really make any difference. So what we're doing is we're just going to count one cycle, and we're running through. We got 16 pulses per revolution. We're running that through a gearbox of 131.25 ratio. So that means 16 gears means that it's going to act like it's got 2,100, right? You understand how we come up with that? Yes or no?
16 times 131.
Yeah, because what we're doing is we're not setting the speed of the motor, we're setting the speed of the output of the gearbox. That's what's driving our load. The motor's not the motor's driving the gearbox, and the gearbox is driving the load. So this thing, we get 131.25 times whatever torque the motor can deliver. But it's going to be at a speed divided by what? 131.25. So it's going to divide the speed by 131.25, but it's going to increase the torque by 131.25. So you can hear the motor is running wide open, but the output shaft is barely turning. But I could stop the motor, but I can't stop the shaft, right? You understand that? Because it's a torque multiplier. Torque multiplier, speed divider. So this is my connection over to the power supply. So I've got my motor connected up to a variable power supply so I can control the speed. And then I've got my encoder connected up to the 5-volt supply because we don't want it to change the speed. Okay. And here's my oscilloscope. And we'll change it up so we can measure it more precisely. Sorry about the fluorescent lights, guys. So now we can see the bottom one, since we're only seeing half of the pulse. We know that the bottom is leading the top one, right? And then if I change directions of the motor, notice the bottom one is lagging because it occurs after. So using that, we could tell what? Direction. Counting the number of pulses, we could tell position. Measuring the time for a pulse, we could measure so what our scope doesn't measure frequency, it measures time. So what I'm going to do is I'm going to make my scope more accurate by spreading it out, so I can't see, so that's the best I can do. And I'm going to measure the time for one cycle. I'm going to speed the motor up a little bit to get it over to here, so it'll be a little easier for us to measure. So we have one cycle from here to there. I have it on 0.1 milliseconds per cycle, for 0.1 milliseconds per division. So each one of these is division. So it'd be 0.1, 0.2, 0.3, 0.4, 0.5, or 500 microseconds. So how fast is the motor running? So y'all want me to go back to the formula? Where is that? I thought it was right here. First of all, my scope doesn't measure frequency, it measures time. We got 500 microseconds. I need to take that time and convert it over to frequency. So how do we take time and convert it to frequency? One over the reciprocal line. I know what you meant. So our time is equal to 500 microseconds. So my frequency would be equal to 1 over 500 microseconds. So what would my speed of the DC motor be? Is that 2,000 RPM? Everybody get the same thing? Well, we can't. Is the frequency 2,000? I don't want to know the frequency. I want to know the speed of the motor. Thanks for telling me that. But I want to know the speed of the motor. So y'all found the frequency. How many teeth did we say it had? 2,100. It didn't sound like it was running at 2,000 RPM. Yeah, the frequency would be 2,000. Or 20 divided by 21, we can knock off 2 zeros real fast, right?
I got 57.1
RPM? So that's not the speed of the motor, that's the speed of the shaft. So if we started counting on the motor and ran this and counted them, then we should have that per our 51 RPM, right? So you're at 51 RPM?
57.
57? Okay, somebody time me. Now ready? For 1 minute, right? 1 minute, right? I'm gonna just count. I'm gonna count out loud, and I should get to 57 when y'all say Are we ready?
You're ready?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57. Is that neat? So I calculated 58, 57 revolutions in what? 1 minute. Pretty good, guys. So if I give you the time, could y'all do this on the test? Huh? Huh? I'm not going to count them anymore, guys. So we know it's accurate, right? Well, wasn't that neat, though? We calculated 57, and I counted 57. So we want to speed it up or slow it down? Okay, we're running wide open. This thing's rated at 12 volts, so I'm going to try to put about 12 volts on there. And what I'm going to do is I'm going to spread my scope out to make it more accurate. So what I'm trying to do is get one cycle. Oh, let's go a little bit faster. So here I have 50 microseconds per division. Can y'all see my time down here at the bottom? 50. So I'm going to count the number of divisions. 1, 2, 3, 4. I've counted in 5. 5, 10, 15, 20, 25, 30, 35. So that's 350 microseconds. And the motor's pretty much well running at its rated speed. It is rated voltage. Oh, y'all waiting on me to put the formula in? Don't y'all know it? Y'all got it? What's that? 350 microseconds. So we take the reciprocal of that, right? That would give us the frequency. We divide that by the number of pulses per revolution, which is 2100, right? Multiply that times 60, and that should give us the speed. Everyone? So I'd have to count a lot faster. 1.6, that's good. 2100 is the number of pulses we get per revolution of the output shaft, which is what we're trying to control the speed of. That's given on this guy that I showed you over here. So at the motor, we're getting 16 pulses per revolution, but we're running it through 131.25 gearbox. So that means we get 200, we get 2,100 pulses per revolution of the output, which is what we want to control the speed of, right? Right. So the motor would be running at, what'd y'all come up with? Times 131.25, that's the speed of the actual motor running the gearbox. But I'm not really concerned with the speed of the motor, I'm concerned with the speed of what the motor is trying to run, right? And this goes through this gearbox. So that's why we multiply the 16. So this encoder gives us 16 pulses per revolution. That's revolution to the motor, that's not revolution to the gearbox, right? So then we multiply that times the ratio of the gearbox, and this gives us the number of pulses we get on the output shaft. This sucker gives us 2,100 pulses for every one revolution of that output shaft. So that's for the 2,100. So we're not calculating the speed of the motor, we're calculating this guy over here. This is the guy where the chain drive would be at or whatever we're trying to run. The encoder, that's what the encoder is giving us. It's giving us 2,100 pulses per revolution. So what we did is we looked at the time for one of the blades on the thing. Then we multiplied that times 2,100. We multiplied that out and gave us the 2,100. Does that make sense? So actually we get 16 pulses per revolution of the motor. But then we run that through a gearbox that divides that by 31.25. So the motor over there gives us 2,100 pulses for one revolution of this shaft.
So like on test, are you
I'm going to give you the time and I'm going to show you the encoder. I think the encoder on the test has 4 blades on it. So it'll give you the time for one blade, right? You understand? Then you multiply it, then you would take the reciprocal of that to get the frequency. Then you multiply that by 4, and then you multiply that by 60. Divide that by 4 and multiply it. And I could tell you the answer, but I'm not. Because some of y'all would remember it, right? You would remember. So what did we look for speed? What was the speed ones we looked at? We looked at variable reluctance, right? You understand? We looked at Hall effect. We looked at DC tachometers, tachmeters, yeah. We looked at AC acts. We looked at incremental encoders. Is that all of them? Probably not, right? And it's very important to be able, on a lot of applications, it's very important to understand that we need to have speed regulation on these devices, right? How many of y'all use the cruise control on your car every once in a while? So you're looking at exactly this situation right there. So either what does it do? It uses the output of an increment encoder, or it uses the output of some sensor that's telling your computer how fast this car is going. So you establish what we call a set point. It compares it to a what? To a feedback. If they match, everything's okay. If they don't match, either it's going to do what? It's going to increase the output of the system, or it's going to decrease the output of the system to make it maintain a constant speed. So, or constant anything. So a closed loop system is a what? That provides feedback, right? You understand? With a sensor. That's one of the main uses for sensors, is to provide that what? That feedback that says something's there, or we tell something to move to a certain position, then we have a proximity sensor says, okay, I'm here, right? You understand? So we'll turn on a conveyor belt, and then we'll turn it off when it gets to a certain position. So this is sensors is the name. Sensors is the lifeblood of closed loop systems. In closed loop systems, this is the lifeblood. Closed loop systems is the lifeblood of automated manufacturing, right? You understand that? Where we tell it to do something, a PLC tells it to do something, but then it needs to know that it's been done before they tell it to do something else. So where are we at on our labs, guys? waiting on me. So I'm doing experiments back there.
We can over there, we ready for you.
Okay. And then we got experiment 3. We got 3 experiments on just the photoelectric. I'm sorry, on the proximity sensors we have. And what we're using now is we're using what? This proximity sensor we're using in this lab is what? Yeah, inductive. And then the next one we'll do is going to be on photoelectric. Now we don't have any capacitive sensors, but if you get the feel of an inductive sensor, you know a capacitive sensor would fit into the same application. So what an inductive sensor only senses what? Metals. A capacitive sensor will sense metals, solid, most solids and some gases. So we can use this, but it's not, you can't say it senses everything. It senses a lot though, right? Are we okay? All right, guys, let's go lab.